Hi, welcome to another episode of The Art of Physics. This one is going to get down and dirty, and so we're going to need some help. Hopefully it won't be too dirty for Bloomfield Community TV. So in order to do that, I have asked a wonderful guest to join us. Our wonderful guest is Bruce Gorman. Bruce,
Hi, Art.
thanks a lot for coming. This is really nice.
My pleasure.
I think we're going to need the help because this is getting dirty here, and so maybe you can clean it up for us just a little.
So what's so dirty here?
We're going to start with one of these things. This is not a commercial. This is oil. Oil, dirty stuff, right? Well, let me show you how dirty it is. One of the problems with oil is the darn stuff will not mix with water. So I brought along a jug of water here, and maybe Jason's going to get a shot of this jug of water. So jug of water filled from the drinking fountain outside, and you know, water is a really good solvent. I mean, it's put all kinds of stuff in solution in water. That's why people drink tea and they add water to their drinks of whatever kind. So, but what about oil? Here's the problem in a nutshell. Let's see if we can do this. Oh, I didn't practice this. There was no rehearsal for this at all, Bruce.
Wow.
Kind of pretty though, isn't it?
Yeah. That's pretty dirty, all right, but we can't see any of the details of what's going on. How about going down to the level where the action is taking place?
You want to get down to the root of the action, huh?
Absolutely.
Well, here, first of all, let me see if I can, maybe I can fix it.
Okay.
Let me try to fix it without even getting down there. Okay, here we go. Ready?
Ready.
I don't want to get on your shirt.
Don't worry.
Nice looking shirt. Okay. See, we'll just mix it up. It'll be fine. Everything will work. There. Thirsty?
No.
Okay. I'm not either.
It doesn't look like it's mixing.
No, it's not. And you know, Bruce, you're right on the money. Bruce knows molecules. And what he knows is we're not going to get to the bottom of this until we get down to the level of what's going on. And what is it that goes on in there? It's molecules that are going on. So, how are we going to get there? It's going to be pretty tough because we're big and molecules are very, very small. So how will we be able to figure that out? Well, I'll tell you. David's going to put in something. Another show has something they call a, what is it that's called? It's a ship of imagination they have. There's the ship of imagination. You can see it there, Bruce. Mm-hmm. That ship of imagination takes them down to the level very small, takes them to distant places, does all kinds of stuff. And so that's all we need is a ship of imagination. However, we have a little bit of a problem. This show has a cheapskate producer, and the cheapskate producer can't afford a ship of imagination. Did you wonder who the producer was?
Who's the producer?
You're talking to him.
Oh, hi.
Hi, I'm the producer. And I'm a cheapskate, evidently. So I do have a substitute, though, and the substitute is this thing. This is called Minion Improbable. And can you see that guy? Ah, there he is. In fact, there's his graphic.
Yes. And
here he is right here. So Minion Improbable will take us down to the level of the molecules.
But can your cheapskate minion get us down to the root of the matter? Molecules?
I hope so. You know, molecules, actually maybe we need to start even smaller. Let's start with the things that make up molecules. Those are the things called atoms. And I think we have a graphic about atoms. There is an atom.
That's an atom?
No. The problem is that that's kind of just a mock-up of an atom, because the atoms are too small. So the net result is, in fact, like any kind of a thing, a model that you make up, this thing is a little bit off. In fact, it's a lot off, because the difficulty is that inside the middle of the atom there's the nucleus, and the nucleus is where most of the mass of the atom is, and the electrons are the things that are going around the outside. So first of all, it isn't accurate in terms of size. If that were accurate in terms of size, the nucleus would be like a bowling ball at the 50-yard line, and the electrons would be zipping around at the level of the goal line. So, and they would be very small because they'd be like flies buzzing around this bowling ball. So that's not a very accurate model. The other difficulty is that that nucleus is positively charged, and the electron zipping around the outside is negatively charged. So the whole thing is electrical. And that's one of the big difficulties. So isn't that kind of a weird picture of an atom?
It is. It is. But there's a lot of empty space in there.
Yeah, there is, exactly. And that's why the big difficulty is. So you know what we're going to have to do? Let's take one level of abstraction up from there. And see with that one level of abstraction up, we're going to actually see if we can't make some models of these atoms. And the atom models are just going to be hard spheres. So we're just going to pretend that those things represent atoms.
Okay.
The difficulty is you can't see the charges, you can't see the vastness of the space inside. So you got, I'm not going to drink this. Get that out of here.
No.
Gosh. You can't get into that deeply. So we're going to have some models of these atoms, because atoms, they're very weird things. You know, I say weird because one of the big difficulties is, you know who studies atoms a lot? Chemistry.
And I've seen those models in chemistry. I remember that.
Yeah, I'm sure you do.
Yes.
And you know, chemistry and I don't get along all that well, but I asked Minion Improbable if he would go and actually find some of those models for me. And so I think if we're lucky, he brought some back. Let's see if that's true, because he brought something back earlier. Let's see if it works. Go back and see your buddy Einstein again, will you? Jeez. So, ooh, he did. He brought back some goodies. Let's see what we can do with these. Whoa, got all tangled up. Atoms are pretty sturdy, and they make sturdy molecules. I say sturdy, that's different than dirty. Not a lot, though. Okay, so why is it that, whoop, gotta save them, gotta do these in the right order. Here's what happens. Atoms tend to either share or give away electrons. Now, if we were studying chemistry, if this was the art of chemistry, I don't know if that exists, the art of chemistry, I'm not sure about that. But if this were the art of chemistry, then we'd be learning all kinds of rules about, well, this atom wants to give away these many electrons, and this atom wants to take that many, and so there's this sharing of electrons between atoms. Oh, man, you know, you can go nuts with that stuff, because there's just all kinds of rules that you've got to memorize.
So I see where you're going. They're sharing and then they're sharing.
You're sure right about that, because, you know, if you had a twin brother, you don't have a twin brother,
No.
do you? Okay. But if you had a twin brother and you shared something, you'd share it pretty evenly, wouldn't you?
Sure.
Yeah, exactly. But let's say that you had a really younger brother.
I wouldn't share.
Either not share at all, which sometimes happens. Do you have a younger brother?
I do have a younger brother.
Does he get anything that you share with him?
Very little.
See? Now that's the way it goes, because they're sharing and then they're sharing, right? Well, here's the funny part. If you have sharing that's even, really even, between the atoms that make up a molecule, then what happens is that the molecule is one which is called nonpolar, because there isn't a spot out at the edge that has some plus, another spot where there's a minus. There's no poles to it. So that's a nonpolar molecule. That's what this one is. This one is oil. So this is a molecule of oil. And you see that it's pretty symmetrical. There is no polarity to it at all. So now here is water. Can you see this one okay? Water, H2O. There's the O, and here are the two H's. Now, do you think the O and the H's share evenly?
Probably not.
O is a whopper.
Yeah.
And so the H's are pretty small. So who wins the battle? Well, the O. So the O wins the battle, so it has a bunch of the electrons around it. So what are the electrons charged? Negative. So here's what happens. You know, if you look at it like this, can you see that okay? That's kind of, this is almost like a Mickey Mouse, right? These are the ears, and this one is the face of the Mickey Mouse. And so if the electrons spend most of the time around here, then the chin's negative. And if the electrons are sort of taken away from there, then the ears are positive. So you got positive ears, negative chin. What does that make? That makes a polar molecule. So here's the problem in a nutshell. You have a polar molecule and a nonpolar molecule. How in the world are they ever going to get together? They aren't, because the only way they get together and make a solution is if you have an attraction of plus for minus. Plus and minus, we know how that works.
So the attraction of positive and negative parts of molecules determines whether the molecules stick to other molecules.
Exactly. And these guys won't stick for shucks. That's why it's like this. They don't stick. So we got a problem here, don't we? What in the world will we ever do in order to be able to get these oil molecules, get the dirt going here somehow? To do that, we're not going to have just water. It's going to take something else.
How about some examples?
Well, an example. Let's see, do we have any examples here? Let's see. How about this? Well, I'll put it to you this way. Suppose that you actually spilled some of that oil. I'm not going to let you do it. But suppose you did. What would you use to get it off?
Detergent.
Detergent. Soap.
Soap.
Something like that.
Yes.
So, happen to have, since Minion Improbable, he may be a cheapskate, but he does bring me some good stuff. This one happens to be a molecule of soap. Now, you look at the molecule of soap, and it looks like, well, this is kind of weird because it's sort of oily like here, but then here, it's got some oxygens. And so the net result of that is that, well, this has some positives and negatives here, doesn't it? That are real, no kidding. Right. But it has on the other end of the molecule some nonpolar. So here's what happens. Gets really weird. If you put detergent or soap in with this oil, then what happens is you get bonding that occurs between the nonpolar ends. So that's fine. But then this polar end is sticking out. Now what happens? Well, now if you got some water and you got these polar ends sticking out that are negative, then you got the positive ears here. Guess what? You can now start to have some kind of attraction going. So now, could we attract this? I mean, this is kind of a whopper, isn't it? Well, let me reveal to you something that actually occurs, and that is there's something that in chemistry they call a micelle, M-I-C-E-L-L-E, and I think we have a graphic of it. Let's see if it comes up here. There's the micelle, and what the micelle is, it's a whole bunch of these detergent molecules that are surrounding an oil. So the oil is encapsulated. I didn't have enough molecules to make this whole thing, but that's what it would take. It would look like that on the screen there. Now, then if you have waters, the waters can now congregate on the outside, and you've got this big whopper of a thing called a micelle with all these waters carrying it along, and it can escort it out. So if I could put detergent in here, then these things would disappear and they would mix. Well, they wouldn't quite mix exactly, but they would be no longer present in an obvious way. So that's the thing that happens, and it's kind of an odd dance, though, isn't it? Because, go back to that micelle again, will you, David? Because the micelle, as you see it there, is big, and it's enough of a whopper that how many of the water molecules do you think is going to take to get them out of there?
A lot.
A lot.
A lot.
So then, if you were trying to do this in some kind of a practical way, what would it take? You'd have to have, to get the oil out, you'd have to have a bunch of detergent, and you'd have to have even more water.
Mm-hmm. Well, okay, well, let's now get down to the practicalities. Let's say if some clumsy fellow like myself spills oil on his clothes. He can't just soak it. The water in it's not going to get the stain out. Wrong kind of molecules.
Yeah, bingo. Exactly. Wow. So then you got to use the detergent, and if you're really clever, you can actually have a machine, too, that works with this whole thing. Put the detergent into the machine.
Like a washer.
Yeah, that would be a good thing, wouldn't it?
Yes.
So then you could actually sort of automate this. But Bruce, you happen to know that these washer things don't always work quite so well, do they? What's their problem?
Well, in today's washers, there's a lack of water. We're so interested in conserving water that the old-time washers used 40 gallons per load. Now we're lucky if they use 11 to 15 gallons a load. So you don't have the water action.
Not enough water.
No.
There's probably a way around that, isn't there?
There is.
What is it?
High-efficiency detergent.
Oh, the high-efficiency detergent then can surround these things a little better, make them easier to flush them out.
It's because it's more concentrated, too. Therefore, in my opinion, it has more molecules to work with the water to get the dirt out.
Well, you know a lot about molecules. How do you know so much about molecules?
Well, back in junior high, I had this great instructor. He taught chemistry. And while chemistry in junior high is a very boring course, many people fall asleep, I was very interested in it.
That's amazing.
And then through the years in high school, went through it then, and I took a course through you at OCC.
Oh boy.
And got the molecular knowledge going again create some interest. And ever since then, I've been a molecular expert.
He has molecules inside his head you can't believe. My gosh, how many years ago was that, Bruce, do you think?
Boy,
That was the 70s, wasn't
it?
it?
35 years ago.
Wow, that's amazing.
Yes.
That is just amazing. Well, you know, Bruce and I have kind of kept in touch a bit over the years, but I always like to Google my guests to find out what the Google says about them. So I Googled you.
Sure.
And here's what I found. Here's the #1 hit that I got when I Googled you. Here it comes. Ready? Watch the monitor there, and you'll see Bruce.
That's when I had hair.
Oh my gosh. So I looked at that for a while and I thought, you know, that probably isn't quite right. So I went a little further. And now let's see what else I found. And this one,
Yeah, that's up to date.
that's more up to date.
Yes.
Now that's you dancing, and you're dancing with this nice young lady that perhaps is related to you.
That's my sister.
That's your sister.
Yes. And we're
Oh.
dancing at my daughter's wedding.
Oh, that's wonderful. That is just wonderful. So Google You actually did work.
It did.
To bring out something
Yes.
worthwhile. Well, that's good. So then, I also happen to know a little bit more about Bruce, and that is I know he has hobbies.
I do.
And some of his hobbies are really interesting ones because he likes Detroit sports teams.
I love Detroit sports teams. In fact, I collect a lot of sports memorabilia.
Ah,
I have attended 3 Stanley Cup parties, courtesy of the Red Wings.
jeepers.
I've gone to a few of the Detroit Tiger parties.
Did you ever touch the Stanley Cup?
I drank out of the Stanley Cup.
Oh, my goodness, that's
Yeah,
wonderful.
it was great. One of the best
But
experiences.
you didn't
I've
drink oil, so
Didn't drink oil, no.
Okay, that's good.
No.
So, wow, that must have been great.
But something that did have to do with chemistry and molecules.
Sure.
Bourbon.
Bourbon. Well, yeah,
Alcohol.
that works very nicely
Yes.
with water.
Yes,
Yeah, because it has a polar end.
it does.
So, what did you think about the Lions game the other day?
Lions game was great.
Wasn't it, though?
Our new head coach, Jim Caldwell, does a great, I mean, he plays that clock to the T. He's a very, very good coach, in my opinion.
Right. And
Yes.
so now maybe we're on the right track.
Maybe.
We get our molecules aligned, and away we
Yeah,
can go.
And we can go to Super Bowl.
Here we come.
Here we come.
So, does Super Bowl have something you can drink out of?
It doesn't.
Ah,
The Vince Lombardi trophy is just
a plain
Just a
trophy.
plain trophy. Nothing, no cup on it.
Ah, darn, that's too bad. Well, there's something else that actually I was able to find out about you, and let's see if we have the next graphic that will show that. And that is
Camp
Michigania. Oh my goodness.
My heart.
Yeah, exactly.
Yes.
How many years have you been going to Camp Michigania?
Over 40.
Wow.
Started with my uncle, and I continued the tradition.
That's fabulous. Wow. Yeah, Camp Michigania is a special place. There
It
have been a
is.
few other guests on this program that have been Camp
Yes.
Michigania people, and oh my gosh. There's a kind of a special bond that goes with the Camp Michigania
Yes.
people. Which week are you?
2.
Week 2.
Yeah.
Oh boy, I'm week 7.
Yeah.
So by the time, see, when you're there, the staff is all new early, and so you have fresh staff.
Correct.
By the time I get there in week 7, the staff's getting a little burnt out. But they're still fun.
They're still friendly.
Yeah,
They're still friendly.
So-
Beautiful atmosphere.
Right. Well, okay. Now, usually the parting words come from Albert Einstein because Albert Einstein is kind of like our patron saint in a
Yes.
way. And so let's see if we have an Einstein Says graphic. And what does Albert Einstein say here? Here's what he says. If I would be a young man again and I had to decide how to make my living, I would not try to become a scientist or a scholar or teacher. I would rather choose to be a plumber or a peddler in the hope to find that modest degree of independence still available under present circumstances. Wow. He wants to be independent.
Independent.
Yeah,
Yes. What a brilliant man.
yeah, nice way to go.
Yes.
So, Albert, here we are. We're in your corner again, buddy. So, listen, thanks an awful lot, Bruce. I sure
My pleasure.
appreciate
Thank
your
you.
coming by. My golly. And to all you people out there, take care, enjoy, and until next time, I'm Art Wiggins.